Welcome to another explainer. Now, if you're sitting there thinking mathematics is just, a boring set of isolated rules and formulas that you just have to memorize, well, I want you to think again. Today, we're going to look at math in a totally different way. We're going to explore it as this dynamic, holistic language. It's literally a powerful tool that we use to decode the intricate patterns, shapes, and systems of the real world around us. And to do that, we're unpacking the fascinating structure of the Cambridge Lower Secondary Mathematics curriculum.
Okay, let's dive right into this. We're going on a bit of a macro to micro journey today. We'll start big with the broad Cambridge curriculum framework. Then we'll zoom in on visualizing inequalities, explore the geometry of angles and intersecting lines, see how we actually draw shapes accurately, and finally, we'll wrap up with symmetry and sequences.
So kicking things off with Section 1, the Cambridge Curriculum Framework and how it builds that crucial foundation for 11 to 14-year-olds.
The whole curriculum is brilliantly structured into 6 distinct mathematical strands. We've got number, algebra, geometry, measure, handling data, and problem solving. Now, the absolute key takeaway here isn't just memorizing that list, it's about how they all interact together. Problem solving isn't just some standalone topic tacked on at the end, it actually underpins the other 5 strands. It gives students the essential structure they need to apply all these diverse math skills to actual, messy, real-world scenarios. Because ultimately, the goal of this curriculum is to develop confident, truly engaged learners. By focusing heavily on underlying principles, recognizable patterns, and whole systems, we're moving students far away from just rote memorization. Instead, they're actively investigating. And that approach, it lays an incredibly solid foundation for the more advanced stages of education coming their way, like the Cambridge IGCSEs.
Which brings us to Section 2, Visualizing Inequalities. This is where we move beyond just single numbers. So, you know how in standard algebra, a letter just stands in for an unknown number, right? Well, what happens when that letter doesn't just equal one single thing? That is exactly where an open interval comes in. By using inequality symbols like less than or greater than, we can actually represent a whole range of numbers. We're no longer just saying, hey, x equals 4. We're saying x could be absolutely anything greater than 4. It's infinite.
And this brilliantly illustrates exactly what we're talking about. Notice that top number line. To show that x is greater than 5, we don't just write down a number. We place an open circle exactly at the 5. That open circle is a clear signal. It means the 5 itself is not included. Then, we draw an arrow pointing off to the right. That arrow is absolutely crucial because it visually communicates that our list of possible integers is 6, 7, 8, 9, and so on, literally forever towards positive infinity. And conversely, looking at the bottom line, it shows y is less than 2, with the arrow pointing left toward negative infinity. Honestly, it's just a beautiful way to map the concept of infinity onto a finite piece of paper.
Okay, let's pivot a bit to Section 3, Angles and Intersecting Lines. We're shifting from the abstract infinity of algebra to the very concrete geometry we see all around us.
Let's walk through these highly visual concepts. Think about what happens when 2 straight lines cross paths. They create a relationship. The angles opposite each other, they are always equal. If those lines intersect, form a perfect right angle, we call them perpendicular. And then when we have 2 parallel lines, lines that will never ever touch no matter how far you stretch them, and we slice right through them with a third line, which we call a transversal, a really distinct pattern emerges. The angles created at the top intersection will perfectly mirror the angles created down at the bottom intersection.
Now, let's see how this all builds together by combining our earlier algebra skills with these geometry rules. In this worked example, we know that the angles on a flat, straight line always have to sum up to exactly 180 degrees. So if we already know one angle is 82 degrees, we can just use some simple algebra to find our missing angle A. 180 minus 82 gives us 98 degrees. And because angle D is vertically opposite to our starting 82-degree angle, well, D has to be 82 degrees as well. We're essentially using logical, step-by-step deductions to unlock the hidden numbers trapped within the shapes.
But how do we actually create those shapes in the first place? That's Section 4, Drawing Shapes Accurately. It's all about hands-on construction.
In geometry, precision is absolutely everything. To construct perfectly perpendicular lines, you can't just eyeball it. You have to follow a precise physical procedure. First up, you start by drawing a totally straight baseline. Second, you carefully align the flat edge of a set square, or the center mark and 90-degree marker of a protractor, exactly along that baseline. And third, you simply draw your intersecting line right up along that vertical edge. Notice how these physical tools are actually manipulated on the paper here. The set square guarantees a true perfect 90-degree angle. and the protractor allows for that exact same precision. By mastering the physical manipulation of these real-world tools, students are essentially learning how to draft the architectural blueprints of reality. They're creating true perpendicular and parallel lines totally from scratch.
So we've seen how to build perfect shapes using geometric rules, and we can easily find patterns within those shapes. But here's a fun question for you. How do we find shapes in patterns? That leads us perfectly into our final pillar, Section 5, Symmetry and Sequences. It's all about discovering patterns so we can actually predict the future.
Let's start with symmetry really quick. A two-dimensional shape like this rectangle has line symmetry, meaning you can fold it in half horizontally or vertically, and both sides are going to match up perfectly. But it also has rotational symmetry. If you were to pin it right in the center and turn it, it would look exactly the same twice during one full 360-degree rotation. In math speak, we say it has a rotational symmetry of order 2. It's a repeating visual pattern.
Now let's take that whole idea of repeating patterns and apply it to numbers and sequences. This is governed by something called the term-to-term rule. This is basically just a descriptive rule that tells you exactly how a sequence changes from one step to the next. For example, if you have 3 dots, then 5 dots, then 7 dots, your term-to-term rule is simply add 2. It is literally the mathematical engine that's driving the sequence forward.
Let's see this applied to a more complex problem. We've got a pattern made of squares here. Pattern 1 has 5 squares, pattern 2 has 7, pattern 3 has 9, and pattern 4 has 11. Now, we have 2 students, Sophia and Marcus, and they're trying to predict the future. They want to know exactly how many squares will be in pattern 20. Take a look at their logic. Who do you think is correct here? Jacob? Actually, wait, scratch that. I mean Sophia or Marcus. Let's figure it out.
So the crucial point is really understanding the difference in their approaches. Marcus, right, he notices the sequence goes up by 2 squares each time. So he simply adds 2 to the target pattern number of 20, and he guesses 22. But Sophia goes a lot deeper. She realizes that to find any term in this sequence, you have to multiply the pattern number by 2 and then add 3. Let's test her logic on pattern 4. 4 times 2 is 8, plus 3 is 11. Boom, it works perfectly. So for pattern 20, she calculates 20 times 2 plus 3, which equals 43 squares. Sophia is absolutely correct here because she used an algebraic expression to define the broader underlying rule rather than just looking at the immediate next step. And that right there is problem solving in action.
And that brings us full circle, right back to the macro view of the Cambridge framework we started with. By mastering these distinct microstrands, whether it's the spatial reasoning of intersecting lines or the numerical logic of sequences and term-to-term rules, students are doing exactly what this quote says. They are developing a robust, holistic understanding of mathematics. They aren't just memorizing formulas, they are actually learning how to actively decode the world.
So, I'm going to leave you with this. Take a look around you today. Where are the perpendicular lines, the transversals, and those hidden term-to-term rules hiding in your own daily life? Because honestly, once you learn the language, you start seeing the math absolutely everywhere. If you enjoyed decoding this with me today, please be sure to hit that like button, share this explainer, and subscribe for more. We'll see you next time.